In this video, we're going to talk about the variations that our jet circulations can have based on the orientation of our isotherms or our isentropes to our jet streak. To begin here, I've redrawn the classic four-quadrant model of our upper-level straight jet streak with a meridionally oriented temperature gradient, a north-south temperature gradient. And so what we have here is our classic four-quadrant model. We have divergence in our right entrance region and left exit region, and convergence in our left entrance and right exit. Again, thinking as we are going along with the flow due to our maximum of our jets in the center, jet max. And so we can maybe even draw a circle around this, maybe a second circle indicating our jet maximum there. The strength of these secondary circulations that are associated with this divergence-convergence pattern are thermally indirect circulation in the jet entrance region and our thermally direct circulation in our jet exit region are going to be directly proportional to how fast the wind is flowing through our jet max, because that is going to be related to then the acceleration of those parcels that are moving through. And so if our overall jet stream is actually moving pretty slow in terms of moving with our trough ridge system, but it has a fast wind speed, that means these circulations are going to be much stronger, which can have a greater impact on the evolution of the synoptic scale flow, and thus then the vertical branches of these secondary circulations. But unfortunately, this situation that we've drawn here for you does not often happen, this perfectly straight jet with our north to south temperature gradients. In fact, what we often have is we have some sort of temperature advection occurring along our jet stream. And so that's what we want to start to identify here with some variations to our jet streaks. And so we're going to start with our straight jet again. So we're just going to draw in our straight jet model. Nothing varying here. Again, 912, maybe 924, 936 in this case. Doesn't really matter, 300 millibar jet stream. But now let's draw in some isentropes that are oriented at a 45-degree angle that would demonstrate cold air advection along our jet core. And so we'll go ahead and draw in a few isentropes here to demonstrate this phenomenon. And so again here, if this is cold air advection, this might be theta, this would be theta minus delta theta, theta plus delta theta, and theta plus 2 delta theta. And so clearly, if in this jet format, right, we have our jet max here, we know that the air flowing through this jet means that this colder air is going to be advected into this warmer air, such that we can say that this setup really is cold air advection. Cold air advection along the jet axis. And so the question is then, what does this do to our overall convergence-divergence pattern, and thus our secondary circulation associated with this jet? Due to this change, we must consider shear deformation within our flow. And as a result, our circulation is going to shift such that it is centered along the center part of our temperature gradient. So for example here, right, we would consider this area between our second and third one to be the center part of our circulation. And so in our jet entrance region, we're still going to get our thermally indirect circulation, but it is now going to be shifted to the south. And so now our new convergence-divergence pattern would look something like this. Convergence right along our jet axis with divergence further to the south. And then in our jet exit region, it's going to shift to the cyclonic side or the north side, and such that we'd have divergence further up and again, convergence directly along our jet axis. This is due to that cold air advection along the jet streak and the resulting shearing deformation that results from this flow. Additionally, along the jet core now, we have convergence, or in general, downward branches of our secondary circulations. This is going to help pull down stratospheric air and help to reinforce upper level fronts and to create stronger upper level positive PV anomalies. So when you're looking at a map, if you see cold air advection along that jet core, that means it's going to be ripe for further development and an increase in strength of that upper level PV anomaly, which then will increase the cyclonic rotation associated with that, with the atmosphere there, which then could strengthen our low pressure systems. So again, this idea of things being all interconnected in the atmosphere. Similarly, we can draw one for warm air advection along our jet axis. Again, using just our straight jet geopotential heights here. Again, 912, 924, 936 for demonstrative heights here. We have our jet max in the middle. But now our isentropes are going to be oriented the opposite way at 45 degrees or so. It doesn't exactly have to be 45 degrees, but are angled down this way such that we're going to get warm air advection along our jet axis. And so now we have, say, our theta plus delta theta, theta plus 2 delta theta, and theta minus delta theta. And so here we do have warm air advection along the jet axis. And so in this case then, our convergence-divergence pattern and our circulations are going to be associated again around the middle part of our temperature gradient, such that then we get divergence along the jet axis and convergence further to the north in our jet entrance region. In our exit region, we'll have divergence along the axis and our convergence further to the south. And so now, along our jet axis, we have rising motion, which is going to start to weaken our upper level positive PV anomalies, weaken our ability to have cyclonic circulations associated with that type of system. And so again, warm air advection along this jet axis would not be conducive to helping increase the strength of our synoptic scale low pressure systems. Finally, what we want to talk about is, are our jet streams often these nice straight jets as we've illustrated here within these variants of our 4-quadrant model? Correct. The answer is no. Sometimes we end up with jet streams that are associated with just troughs, for example. And so here's an example of some cyclonic curvature that we do have a jet streak here in the middle. Not terribly well drawn by me, but we can see that there'd be some sort of jet here, such that the question is, we now no longer have that anticyclonic curvature on the south side. And so it becomes more problematic to identify what's going to happen. And so for the most part, on our cyclonic side, it would work the same as for our straight jet, such that we had to have convergence here. And again, if we had advection, it'd move it a little bit more north, and divergence in our exit region. But what would happen to the south becomes more problematic and more peculiar based on each individual circumstance, since we don't necessarily have that anticyclonic vorticity to our south as we do in our straight jets. And so our ageostrophic circulation is going to be a little bit more unclear. That's it. That's it for variations on our jet streams. What we'll talk about in future videos are the different types of jets we can see in the atmosphere and what are some of the common characteristics associated with them. Thanks for watching.